In today's assignment, we will be looking at extrinsic semiconductors. Assignment 3. In assignment 2, we focus exclusively on intrinsic or pure semiconductors, and today we will be looking purely on extrinsic semiconductors. So, before we look at the numerical problems, let me do a brief recap. Extrinsic semiconductors are also called doped semiconductors. So, the whole process of doping is to selectively increase your carrier concentration, so either N or P. The law of mass action is something that has to be obeyed. So, Ni square, where Ni is your intrinsic carrier concentration, must be equal to Np. So, if we dope with donor type impurities to increase the concentration of electrons, so if N goes up, P has to go down, and similarly if P goes up by doping with acceptors, then N has to go down. We also saw the conductivity equation last time. Sigma is Ne mu E plus Pe mu H. In the case of an extrinsic semiconductor, we usually dope such that either N is much greater than P or P is much greater than N. Either way, only one of these terms will usually dominate. So, the conductivity will be either due to the motion of electrons or due to the motion of holes. In the case of an extrinsic semiconductor, once again because we do not have equal number of electrons and holes, the Fermi level will shift from the center of the gap. It will shift closer to the conduction band for an N type semiconductor and closer to the valence band if it is a P type semiconductor. This will also depend upon the temperature and whether all the donors or acceptors are ionized. So, these are some of the concepts that we will touch in today's assignment. So, let me look at question 1. So, we have a group 4 semiconductor is doped with donor atoms Nd. The donor atom concentration is 10 to the 18 per centimeter cube. The intrinsic carrier concentration is given. So, Ni is given 2.3 times 10 to the 13 per centimeter cube. The values of Nc and Nv, the effective density of states, is also given. So, Nc equal to Nv equal to 7 times 10 to the minus 10 to the 19 per centimeter cube. So, the sample is essentially at room temperature. So, temperature T is 300 Kelvin. So, the first question says what is the hole concentration at 300 Kelvin. So, it is doped with donor ions. So, it is an N type semiconductor. So, N is equal to Nd. At room temperature, the impurities are usually fully ionized. So, N is equal to Nd equal to 10 to the 18. To calculate the hole concentration, we can use the law of mass action. So, Np is equal to Ni square. The value of Ni is also given. So, P works out to be 5.3 times 10 to the 8 per centimeter cube. So, the concentration of holes is much smaller. So, nearly 10 orders of magnitude smaller than that of the electrons. what is the band gap of the semiconductor. So, to calculate the band gap, we can actually use the intrinsic equation which we saw in assignment 2. So, Ni is Nc Nv exponential minus Eg over 2 kT. So, Nc and Nv values are given, temperature is known, Ni is known. So, the only thing that is remaining is Eg, and Eg is 0.772 electron volts. We can sort of make a guess that the material is germanium, but germanium usually has a band gap of around 0.67. Of course, in this particular problem we have taken Nc is equal to Nv, and that is not true for germanium, but this is the band gap. The band gap is a low value, you can see that because Ni is around 10 to the 13. For pure silicon, the value of Ni at room temperature is 10 to the 10. So, we have calculated the whole concentration and also the band gap. Then we want to know the position of the Fermi level in the doped semiconductor with respect to the intrinsic Fermi level. So, EFN minus EFI. So, EFN is the position of the Fermi level in the n type semiconductor, EFI is the position in the intrinsic semiconductor, is nothing but kT ln of n over Ni. In this particular case, n is nothing but Nd. So, we can substitute all the values, we can use k in the SI units, but then we need to divide by 1.6 times 10 to the minus 19. So, that we convert it back to electron volts, and if you do this, EFN minus EFI is 0.276 electron volts. In this particular case, Nc is equal to Nv. So, we can also calculate an absolute value for EFI, which is nothing but Eg over 2. Eg is 0.772. So, this is nothing but 0.386. So, we can substitute for the value of EFI in here and get the position of the Fermi level with respect to the valence band as well. So, let us now move to question number 2. So, we have a semiconductor with the value of Ni. So, Ni is 10 to the 16 per meter cube. So, this we can keep as meter cube, or we can convert it to centimeter cube. So, this will be 10 to the 10 per centimeter cube, but for now we will just work with per meter cube. A semiconductor with Ni equal to 10 to the 16 per meter cube is doped with acceptor impurities. The concentration of acceptor impurities is also given. So, acceptor impurities the value of Na, and that is 10 to the 23 per meter cube. So, donor impurities basically produce electrons. If we go back to the class, donors are typically group 5 elements. So, if we think about silicon, donor impurities are phosphorus, arsenic, antimony, which donate the extra electron. Acceptor impurities are elements like boron, aluminum and gallium, which accept the extra electron from silicon and create a hole. So, acceptor impurities produce excess holes, donor impurities produce excess electrons. So, we have acceptor impurities. So, once again we want to calculate the electron and hole concentration. So, the temperature is given it is 300 Kelvin. So, Na is fully ionized. So, all the acceptors are ionized. So, P, which is the whole concentration, is equal to Na, is equal to 10 to the 23 per meter cube. N, we can again use the law of mass action. N is equal to Ni square over P. So, we can do the numbers. N is 10 to the 9 per meter cube. If you want to convert these to centimeter cube, divide by 10 to the 6. So, this is 10 to the 3 per centimeter cube, and this is 10 to the 17 per centimeter cube. Assuming that the effective masses, so in part B, so assuming that the effective masses of electrons and holes are equal to the free electron mass, calculate Eg, the band gap, and Ef, the position of the Fermi level. So, this is part A. In part B, we are given that Me star, which is the effective mass of the electron, this is Mh star, is nothing but Me. Me is the rest mass of the electron. So, once again we have to calculate Eg. We know the value of Ni. So, Ni is square root of Nc Nv exponential minus Eg over 2 kT. The thing here is we are not given the values of Nc and Nv, but these can be calculated from the mass of the electrons and holes. So, Nc is nothing but 2 times 2 pi Me star kT over h square whole power 3 over 2. Nv is 2 times 2 pi Mh star kT over h square whole power 3 over 2. So, Me star and Mh star values are given, they are equal to the mass of the electron. So, we can evaluate Nc and Nv. So, Nc is equal to Nv and it is equal to 2.5 times 10 to the 25 per meter cube. So, you can convert this to centimeter cube as well, you will just have to divide by 10 to the 6. So, now we know the values of Nc and Nv. Ni is known, Ni is given to be 10 to the 16. So, we can go ahead and calculate Eg. The value of Eg is 1.12 electron volts. Once again, the material that we are talking about here is silicon. You can clearly see that Ni is 10 to the 10 per centimeter cube, which is what the room temperature intrinsic carrier concentration of silicon is. So, we now have to calculate the position of the Fermi level. This is a p type material because we have acceptors rather than donors. So, in the case of donors, the Fermi level moves closer to the conduction band. In the case of acceptors, the Fermi level moves closer to the valence band. So, EFP minus EFI is nothing but minus kT ln of P over Ni. So, P we know, Ni is known, we can substitute and this is minus 0.42 eV. So, this is below the intrinsic Fermi level and it is minus 0.42 eV below the Fermi level. We can calculate the value of EFI. EFI is nothing but just Eg over 2. So, Eg is calculated to be 1.12. So, EFI is 0.56. So, that we can substitute here, and that gives you EFN is nothing but EFI minus 0.42, which is 0.14 eV above the valence band. So, in a way, problem 2, the part B, is very similar to what we did in problem 1, except that now we all have acceptor impurities instead of donor impurities. So, in part C, question says donor impurities are now added to a concentration of 5 times 10 to the 22. What are the new values for the 4 quantities calculated above? So, we now add donors and the concentration ND is 5 times 10 to the 22 per meter cube. The sample already has acceptors. Acceptor concentration Na is 10 to the 23 per meter cube. So, this is an example of compensation doping, where we have both donors and acceptors. In this particular case, Na is greater than Nd. So, ultimately the material becomes p type and the concentration of holes is just Na minus Nd. So, P is 5 times 10 to the 22 per meter cube. N we can calculate as before, again using the law of mass action, Ni square over P, which is 2 times 10 to the 9 per meter cube. We can go ahead and calculate the position of the Fermi level. So, EFP, we can repeat the calculations that we did before, except using the new values of P. So, EFP if you calculate becomes 0.16 electron volts above EV. The band gap will not change because the band gap is calculated based on the intrinsic values, but because the values of P and N change, the position of the Fermi level will change. So, let us now move to question 3. Question 3, using the hydrogenic model, how much energy is required to ionize a donor atom in a semiconductor with a dielectric constant of 10 and an electron effective mass that is only 30% of the free electron mass. So, we looked at the ionization energy of a donor or an acceptor earlier. We found that these donor levels are close to the conduction band and the acceptor level is close to the valence band, and typical ionization energies are of the order of tens of milli electron volts. This is why these levels are usually fully ionized at room temperature. So, to look at the ionization energy EB, we typically use a hydrogenic model, but we modify the mass of the electron and also the dielectric constant. So, the equation for that is something similar to what we worked out in class, is minus 13.6 Me star over Me times 1 over epsilon r square. This answer will be in electron volts. So, 13.6 is the ionization energy for the hydrogen atom. This value is in electron volts. Me star over Me is nothing but the electron effective mass. In this particular problem, it says the electron effective mass is 30% of the free electron mass. So, Me star over Me is 0.3. Epsilon naught R is the relative permittivity of the semiconductor. So, again for this particular problem, the permittivity or the dielectric constant is given as 10. So, we have all the values that we need. We can substitute that and evaluate EB, and EB if we calculate comes out to be minus 41 milli electron volts. So, this is the ionization energy of the donor atom. So, this is the energy that is required to remove the electron from the donor atom and take it to the conduction band. For comparison, the thermal energy of an electron at room temperature is 25 milli electron volts. So, at room temperature it is possible to easily ionize the donors and take the electron to the conduction band. In the next problem, in problem 4, we will look at those calculations explicitly. In part 2 of problem 3, we also need to calculate the Bohr radius of the donor atom. So, once again we are using the hydrogen model and we want to calculate the Bohr radius. In the hydrogen model, the Bohr radius A naught is given by the expression epsilon naught h square over pi Me and E square. So, this is again based on calculations, and the Bohr radius works out to be 0.53 angstroms. So, in this particular case we can use the same expression, but epsilon naught. So, for the donor atom, the Bohr radius, I am going to call it A naught prime, is nothing but epsilon r epsilon naught h square. So, we replace epsilon naught by epsilon r times epsilon naught, and Me is replaced by Me star. So, the expression is the same except that we are adding the dielectric constant and also the electron effective mass. So, we can plug in these numbers and this gives you a Bohr radius of around 18 angstroms. The way to think about this is that this represents the influence of the donor electron. So, it represents a size of the influence of the donor electron. So, in the case of an extrinsic semiconductor, we usually treat these donor levels as individual atomic levels. So, the concentration is usually of the order of parts per million or parts per billion, so that we treat them as individual atomic levels. But if we keep on increasing the concentration of the donors, then these atomic levels will come together, and when two donors see each other, which means when the distance between them comes to be less than 18 angstroms, then they will start to interact and they will form a band. At usually these high concentrations, donors form, instead of single atomic levels, a donor energy band which can then overlap with the conduction band. So, these types of semiconductors are called degenerate semiconductors. So, to calculate the number of dopants or the dopant concentration when we have degenerate semiconductors, so I will call it donor overlap. it is nothing but 1 over the volume of the dopant atom I will put the word atom here within parenthesis to actually talk about the sphere of influence of your donor. So, this is nothing but 1 over 4 by 3 pi A naught prime cube. So, this particular value works out to be 4.1 times 10 to the 19 per centimeter cube. So, at this concentration and at higher values of concentration, your donor atoms are essentially too close, so that the atomic levels mingle and we have a donor band. So, this determines the conditions for forming a degenerate semiconductor. So, when the concentration is greater than 4.1 times 10 to the 19 per centimeter cube, we get a degenerate semiconductor. So, this is a simple back of the envelope calculation where we use the effective Bohr radius of the donor atom to calculate the concentration where we get a degenerate semiconductor. So, let me now go to problem 4. With 10 to the 15 phosphorus atoms. So, phosphorus is a donor. So, Nd is 10 to the 15 per centimeter cube. The donor energy level for phosphorus in silicon is 0.045 eV below the conduction band edge. So, delta E, which is your donor ionization energy, is 0.045 eV or 45 milli eV, and this is below the conduction band. So, Cb is your conduction band. So, where is the Fermi level located? At 0 Kelvin. So, T equal to 0 Kelvin, we want to know the position of the Fermi level. So, at low temperatures, if you think about the model, so let me draw a schematic of the band diagram. This is EC, this is EV, the material is silicon. So, your band gap is typically 1.10 electron volts. We have a donor level that is very close to the conduction band edge. So, this is your donor level and this energy is 0.045 eV. So, the diagram is not to scale, but this just shows you that the donor level is very close to the conduction band. So, at 0 Kelvin the donor level is not ionized. So, we basically have electrons here. The valence band is at a much lower energy level. So, we can sort of ignore the valence band and we can treat this as an intrinsic semiconductor with the donor level being the valence band and the conduction level being the conduction band of silicon. So, in this particular case EF will be located between the donor level ED and the conduction level EC. So, this is nothing but your donor level. So, let me mark that here as ED, and the temperature is 0 Kelvin. So, if you use this expression EFI is Eg over 2, minus kT ln. So, 3/4 kT ln Me star over Mh star. Temperature is 0 Kelvin. So, this term goes to 0. Eg is nothing but delta E, which is 0.04 Y electron volts. So, that EFI is half of that. So, 0.225 electron volts, or right in the middle of the donor level and the conduction band. So, at what temperature? So, this is part A. In part B, at what temperature is the donor 1% ionized, and where is the Fermi level located at this temperature? So, we start at 0 Kelvin, where we have a donor level that is not ionized at all, and a conduction band that is completely empty. We then start to increase the temperature, so that electrons from the donor level start to move and occupy the conduction band. So, we can again treat this as an intrinsic semiconductor. So, concentration of electrons is nothing but Nc Nd over 2, and the reason for the 2 is because these are individual atomic states. So, they can only take one electron, minus Ed or minus delta E over 2 kT. So, we are using the expression for an intrinsic semiconductor, except that instead of writing Nv, we write Nd over 2, and delta E is the ionization energy. N, the question says, is 1% ionized, so 0.01 Nd. So, everything else is known except for the temperature. So, this we can substitute in. So, temperature we can calculate to be 29 Kelvin. So, all we have done is to take the expression for an intrinsic semiconductor and then modify it. We can calculate the position of the Fermi level. So, EFI, once again we can use the expression for an intrinsic semiconductor. So, it is delta E over 2 minus 1/2 kT, and we will use the effective density of states. So, ln of Nc over Nd over 2. So, once again if you plug in the numbers, this works out to be 10.1 milli electron volts, and this is above Ed. So, let us look at part C. Part C asks, at what temperature does the Fermi level lie in the donor energy level? So, when the Fermi level is complete, when the donor is completely ionized, EF will be at Ed. So, EF will be equal to Ed when the donors are completely ionized. So, once again N is equal to Nd, which is square root of Nc Nd over 2 exponential minus delta E over 2 kT. So, everything else is known except for the temperature. So, the temperature gives, calculation gives you a temperature of 61.3 Kelvin. So, at a relatively low temperature of around 60 Kelvin, you get the donors to be completely ionized. So, estimate the temperature, part D, estimate the temperature when the sample behaves as if it is intrinsic. When the sample behaves like an intrinsic semiconductor, N is around 1.1 Nd. So, if you go back to the notes, we say that the sample is intrinsic when the electron concentration is 10% more than the donor concentration. So, we have a regime between saturation, and this is your saturation temperature, and the intrinsic temperature, where the concentration of electrons is within 10% of the donor concentration. So, N is 1.1 Nd, P is nothing but 0.1 Nd. This is something we can get by just doing a charge balance, so that the net positive charge must be equal to the net negative charge. Np is Ni square, which means Ni is 0.33 Nd. This is your intrinsic carrier concentration. So, this is now Nc Nv, and these are the conduction and the valence band of the silicon minus Eg over 2 kT. So, we can substitute the numbers. Temperature T is around 618 Kelvin. So, the question also gives you the density of states. So, you know the value of Nc and Nv, Eg is known. So, the only thing that is unknown is temperature. So, this temperature T is called your intrinsic temperature. This is called your saturation temperature. So, that between the saturation and intrinsic, your concentration of electrons, which is your majority concentration, is within 10% of the donor concentration. Part E, you are asked to sketch a schematic . So, in part E, sketch schematically the change in Fermi level with temperature. So, let me just draw it here. So, this is your conduction band Ec, this is the valence band Ev, these are my donor levels Ed. So, just for schematic, let me take this to be a temperature axis, and this is the center of the band gap Eg over 2. So, at 0 Kelvin your Fermi level starts to be here. As the temperature rises, electrons start to go from the donor level to the conduction band, the Fermi level drops. At some particular temperature, which is Ti or Ts, the saturation temperature, the donors are completely ionized, and then the Fermi level starts to fall down, and at really high temperatures it becomes equal to Eg over 2. So, this temperature is Ti, and within this particular regime your electron concentration is almost a constant. So, let us now look at the fifth problem. So, we have an N type silicon which is doped with phosphorus atoms. So, Nd is 10 to the 17 per centimeter cube. The drift mobilities of electrons and holes in silicon depend upon the total concentration of the dopant, and the expression is also given. So, usually we take the drift mobility to be a constant, but actually with increase in doping, especially in extrinsic semiconductors, the mobility actually decreases. We have seen this in class. This is because we have the electron or the hole being scattered by the ionized donor or the acceptor. So, in this particular case mu E is given to be 88 plus 1252 divided by 1 plus 6.984 times 10 to the minus 18 N dopant. The units are centimeter square per volts per second. So, in the first part we want to calculate the room temperature conductivity. So, we know N is equal to Nd, it is an N type semiconductor. So, P is Ni square over Nd, is usually much smaller than N. So, if it is silicon, Ni is 10 to the 10. So, we can actually work it out, P comes to be 10 to the 3. So, in this particular case conductivity sigma is Ne mu E plus Pe mu H, P is much smaller than N. So, this term goes off. So, this is nothing but Ne mu E. So, we can plug in the numbers to calculate mu E, we plug in the dopant concentration which is 10 to the 17 and you get the value of mu E. So, if you do that, the value of sigma comes to be 13.2 ohm inverse and centimeter inverse. In part B, we want to do compensation doping in this system. So, we are going to add acceptors to make this sample p type with having the same conductivity value. So, now we have a p type semiconductor and we do this by adding acceptors Na, and this must be greater than the donor concentration Nd. So, P in this case is nothing but Na minus Nd, and conductivity sigma is Pe mu H. So, there is a similar expression for mu for the p type or similar expression for the mobility for the holes. Mu is 54.3 plus 407 1 plus 3.745 18 N dopant. So, the important thing to remember here is that this is the case where we have acceptor and donor impurities. So, the total dopant concentration in part B is equal to Na plus Nd. So, we use the same equation sigma, it is now p type. So, it is Pe mu H, P is nothing but Na minus Nd and Nd we know, mu H we can use this expression except that N dopant will be Na plus Nd. So, what we have is an equation where everything is known except for Na. You can simplify this expression, I will not go through the math, but this is essentially a quadratic equation which you can solve, and when you solve you get the final value of Na, and the value of Na is 3.04 times 10 to the 17th. So, this is greater than the value of Nd which is 10 to the 17th. So, what you have is essentially a p type semiconductor where you have done compensation doping by adding excess amount of acceptors. So, the main point here is that when you have whether an N type or a p type, the conductivity is essentially determined by the majority charge carriers.